Hi, I'm Matthew Cooper from Dalhousie University, and I've been working with the Canoe project on air quality monitoring. And my presentation today is going to be about work that our group's been doing at Dalhousie, looking at how we can monitor NO2 air quality from space. So NO2 is an important air quality hazard. Exposure to elevated concentrations of NO2 have been associated with increases in asthma diagnoses, respiratory disease, lung cancer, and overall mortality. On top of that, NO2 is also a primary pollutant that leads to the production of ozone and nitrate aerosols in the atmosphere. Both of those have their own air quality impacts. And so NO2 ends up being really important for atmospheric chemistry and air quality. Most of the NO2 in urban environments comes from the burning of fossil fuels, and that's largely through vehicle exhaust. And we often use NO2 concentrations as kind of an indicator for how transportation impacts air quality in a region. The good news is that over the past several decades, NO2 concentrations have been decreasing. This figure from the CCME air quality report shows that in Canada, we've been kind of steadily decreasing over the past several years, so that's great. And part of the reason why this can happen so quickly is that NO2 has a short lifetime, and so it can respond very quickly to changing emissions. Health studies that try to look at how NO2 impacts health outcomes are often reliant on ground monitor data. But unfortunately, there's a lot of regions of the globe that don't have adequate air monitoring going on. This is a figure from the OpenAQ project showing publicly available NO2 monitors around the globe. You can see that in some regions, there's really good high density observations, but a lot of regions there aren't. And even in a place like Canada, where we have really good NO2 monitoring relative to other countries, this figure shows the location of the NAPS NO2 monitors in Canada. We still don't know a lot about what's going on in between these monitors. And many studies that have looked at NO2 concentrations across a city, for example, Toronto, will show that NO2 concentrations can vary quite dramatically in space. And even if you had a handful of monitors in a given city, which is rare, you still won't be able to capture everything that's going on in NO2. And so we really need another way to be able to monitor NO2 concentrations. One thing that can help fill those gaps are satellites. And so this is a figure, it's a really nice one from the European Space Agency showing satellite observations of NO2 columns from the TROPOMI satellite instrument, which has been providing data since 2018. You can see how there are some really strong spatial gradients in NO2 around the globe. You can see these hotspots over the major cities, enhancements over transportation routes, and over oil and gas production regions. And so these satellites can be really useful for filling these gaps. A problem is that getting a surface concentration from these satellite observations is a complicated problem. From an air quality and public health perspective, what we're interested in is how much NO2 is at the surface where people are living and breathing. But what a satellite tells us is how much NO2 is in the atmospheric column, meaning between the surface and the satellite. And those two quantities are not quite exactly the same thing. So it's important to be able to figure out how they relate to each other. And the way we can do this is by taking information about the vertical distribution from a chemical transport model. So in our research, we use the GeoSCAM chemical transport model, which essentially is a computer model that takes in the NOx emissions and the weather conditions to move that nitrogen around in order to simulate vertical profiles of NO2. And some examples of those are shown here, where you can see that in an urban region, because of the large pollution sources, most of the NO2 is down near the surface, whereas in more rural regions, the NO2 tends to be more well mixed throughout the atmosphere. And in remote regions, it can even be really low at the surface and higher aloft because of long range transport. And so we need to have this vertical profile information in order to convert the satellite columns into a satellite-based estimate of surface concentration, which is what we're interested in. And so we use these profiles and observations from the TROPOMI satellite to infer ground concentrations across Canada for 2019. This is the annual mean concentrations for 2019 on a 1 by 1 square kilometer grid, which is a much finer resolution than any previous satellite estimates of surface NO2 have been produced at. And we can see really clearly that there's a number of hotspots over the region. You can see the major cities popping up. You can see elevated concentrations in the oil production regions in Alberta and BC. You can see some outlines of highway routes and industrial corridors along those highways. And we can make comparisons between these TROPOMI-derived estimates and ground monitor data that exists in Canada and the US. And we can see a really strong agreement between the two that the satellite-derived estimates are very consistent with the ground monitors, which allows us to have some confidence that these satellite-derived estimates can be a useful tool for monitoring NO2 distributions. And of course, we can extend this beyond just looking at Canada and take a global perspective. And that's what I'm showing here, again, the annual mean at 1 by 1 square kilometer resolution globally, which is a really useful tool, especially in regions where there is no NO2 monitoring or a lack of NO2 monitoring. And this could be really useful for understanding the health impacts of NO2 in these regions as well. Now, because NO2 has a really short lifetime, it's able to respond really quickly to changes in emissions. And this has been a frequently discussed topic in the last year or so as these travel restrictions laid into place to help prevent the spread of COVID-19 have led to restrictions on travel, which has led to restrictions or reductions in NOx emissions from transportation and other sectors, and that has led to decreases in NO2. And so we can use our satellite-derived surface estimates to examine these. So what I'm showing here is a map of the monthly mean concentrations globally for April 2020 compared to April 2019. And what stands out is that in many regions of the globe, particularly urban areas in North America, Europe, and East Asia, we see really significant decreases in NO2 concentration in 2020 compared to 2019. But an important thing to consider is that there's lots of different reasons why NO2 concentrations could change one year to the next. And one of those is weather, because NO2 concentrations are really dependent on weather conditions. For example, wind speeds, temperatures, boundary layer heights, and things like that affect how quickly NO2 can disperse in the atmosphere. And so it's possible to have a big year-to-year difference just because the weather conditions were more favorable one year than the next. And so it's important to understand how that's whether that's happening. Another thing is that our satellite observations themselves are affected by weather because satellites can't see through clouds. And so if there's a lot of clouds one year compared to another, that could impact things as well. And so it's important to take these things into account when we're trying to find out whether these lockdowns impacted NO2 concentrations. We can do that using the geoscience chemical transport model again, because the model knows what the weather was like, but it doesn't know how emissions change because of lockdown. And so any changes that we see in a geoschem simulation are estimating how those concentrations would have changed if there weren't lockdowns. And so we can see by comparing April 2020 and April 2019 from TROPOMI and from our simulations that, especially in the Southern Ontario region, we see some really strong decreases in our satellite observed surface estimates. And our geoschem simulations show that there likely, even if there weren't lockdowns, probably would have been some decrease in NO2 anyway, just because of the more favorable weather conditions in 2019 for producing high concentrations of NO2. But what we see is that the expected change because of the weather conditions was not as large as what we ended up having. And that indicates that the lockdowns really did have an impact on NO2 concentrations in that region. Of course, we can do this for all the countries in the globe and examine how NO2 changed. And I'm showing some examples of these countries in this figure here, where each row is a different country. The first column is the change in population-weighted NO2 concentration in 2020 compared to 2019. The middle column shows the expected effects due to different weather conditions, and the right column shows the expected long-term trends in NO2, because in a lot of places of the globe, like I said, NO2 concentrations have been going down as of recent years. But what stands out is that the observed change in pretty much every case is much larger than what we would have expected from meteorology and much larger than what we would have expected from the long-term trends. So for Canada, we see that the population-weighted NO2 concentration was about 31% lower in 2020 than it was in 2019. And if we were to look at what the expected change was because of meteorology, we would have expected a small decrease anyway, maybe 17% decrease. But obviously our observed decrease was much larger. So the lockdowns really did have an impact. If we look globally and compare the observed difference in 2020 and compare that to the long-term trends, we see that the change in 2020 was about 12 times bigger than the usual interannual decrease. And so these lockdowns really did have a substantial impact in accelerating the decreases in the trends that have been going on in the past few years. We can also do this for looking at city level changes. I looked at more than 100 cities worldwide, and we can produce a similar sort of plot here where, again, each row in the figure on the right is a different city. We can see most of the observed changes are negative, meaning 2020 concentrations were lower. And in most cases, those concentrations are lower than the expected meteorological effects or the long-term trends. The bar graph on the left is kind of just summarizing all of these cities. And we can see that the average change in 2020 compared to 2019 was about 33%. The expected change because of weather was around 0, and the long-term trends we would have expected decreased about 2%. So again, NO2 concentrations have been going down in recent years anyway, but the change we saw in 2020 was much, much larger than what we would have expected. If we look at some individual cities, we saw that the biggest change globally was actually in Lima, Peru, which had an 87% decrease in 2020 compared to 2019. If we rank the 200 or so cities that I looked at, Toronto landed about 38th overall with a 67% change, and that's the largest change in North America. And so we do see the impact that lockdowns had in Toronto. In Calgary, we also see a 41% decrease. But if you look at these time series here that I've chosen for some other cities in Canada, we can see, again, the big decrease in Toronto in April and a significant decrease in Calgary. But Vancouver, Montreal, and Edmonton all had changes between 2020 and 2019 that were relatively small. And that is likely an indication of how accurate the satellite-derived surface estimates can be. Not necessarily saying that there weren't lockdowns in these places that were effective, but that the changes were small enough that they weren't statistically significant in our satellite-derived estimates. So in summary, our group has developed this method of deriving ground level concentrations from satellite columns. And our new estimates are at a higher resolution than any previous ones have been, significantly higher at 1 by 1 square kilometers, and that these estimates really agree pretty well with the ground monitor data, which lends confidence in their usefulness. We use these estimates to look at changes during COVID-19 lockdowns and saw consistent decreases across the globe. Canada population decreased by about 31%, and especially large in Toronto. And this is really an excellent case study for how this data can be used to monitor the spatial distribution of NO2 and how these satellite-based estimates could be really useful in health impact studies for giving spatial distribution of NO2 and helping exposure estimates.